Hi, so we're going to start talking about isotopes and atomic mass now. Okay, so isotopes might be a new word for you, but isotopes are just atoms of the same element that have a different number of neutrons. So protons and electrons are the same, just the neutrons are different. So you might have heard of carbon-14 before. That's the name of a really rare isotope of carbon that gets deposited over a specific amount of time. Um, And so once things stop growing, we can use that to date things like archaeological finds. So things like pottery and remains of civilizations. And we can even use it to carbon date animals up to a certain point when they're fossils. But once it gets to beyond that point, we have to move to a different isotope of a different element. So carbon-14 is really useful. And it's useful just because it's so rare. And so carbon-14 is a kind of carbon that has 6 protons, 8 neutrons, and 6 electrons. Okay, so let's look at identifying isotopes when we're looking at text. Now what you see here are 2 examples of isotopes written as symbol notation. Okay, so these are the chemical symbols, or the element symbols, and then the isotope notation. So the top number is your mass number. So remember, mass number is the number of protons plus neutrons. And then the bottom is your atomic number. So that's just the number of protons. Okay, that also identifies the element. If we were to write out the name of these isotopes, they would be copper-63 for the mass number 63 and copper-65. And we read those as copper-63 and copper-65. You don't have to say the dash in between, but you write it with the dash. And so the only difference between these 2 isotopes is that copper-65 has 2 more neutrons than copper-63. They'll both behave exactly the same chemically. Okay. Um, so now we're going to take a look at calculating atomic mass. So what is atomic mass exactly? Atomic mass is measured in AMUs. 1 AMU is equal to 1/12 of a carbon-12 atom's mass. This represents the combined mass of 1 electron, 1 proton, and 1 neutron. However, electrons are so small that when we're calculating things like mass number, we ignore them. So things like copper-63 and copper-65 have those whole number mass numbers. We don't include electrons in that. We only include electrons in atomic mass, and we only include them when we're looking at whole atoms. So this is the equation to calculate your average atomic mass. The symbol in the middle here, that means the sum of. So we would read this as average atomic mass is equal to the sum of the isotope mass times the isotope abundance for each isotope of an element. Okay. And so all this symbol here in the middle means is that you're going to repeat the stuff in the parentheses for every isotope. Then you're going to add them all together. So I'm actually going to switch over to the whiteboard because it's easier to write in the steps and show you what I'm talking about. My apologies for the sniffles. There we go. Ooh, hey. Do that. Okay. Okay. So to calculate atomic mass of an element from isotope data, you're going to start with this little table here. And there we go. So you're going to start with this table right here. And what that is that is isotope data. So we have an unknown element here as an isotope 6 and an isotope 7. So we have an AMU of 6.015 and 7.016. Okay, because it's an unknown, we don't have that atomic number on the bottom there. And then it has their percentage of abundance. So the percent abundance is 6x is 7.59% abundant, and 7x is 92.41% abundant. So the first thing we need to do is turn that percent abundance into a decimal. And you do that by just dividing that percentage by 100. So we're going to do the same. So here's the example. Equals a decimal. Okay. So now we're going to do the same thing over here. So 7.59 divided by 100 is 0.0759. 92.41 divided by 100 is 0.9241. Okay. Now we're going to write out the equation to include all isotopes. So I'm going to shorten the equation a little bit. So it's average atomic mass. Okay, I just shortened to average so I don't have to write so much. Equals the sum of, and I have a hard time drawing that, so it's going to be messy. And we're going to put in, just starting from top to bottom, 6 and 7. So 6 has a mass, so isotope mass, and I'm just going to put a little 6x here, plus isotope abundance, because we're doing this all as a word equation first. 6x there. And then because this says sum of, this is a plus. And then we're going to do the same thing, isotope mass. And this is going to be for 7x times isotope abundance 7x. Okay, now this one only has 2 isotopes. If there were more isotopes, you would keep going until you ran out of data. So now we're going to plug in the number. So we're going to keep this as average atomic mass equals sum of, and now for isotope mass X, we're going to pull from right here. So that's going to be 6.015. And this should be a multiplier right here. That should be multiplied. And then we're going to multiply by the decimal that we did in step 1. So that would be 0.0759. Then we're going to fill in the blank for 7x. So a mass is 7.016 times this decimal that we calculated up here, which is 0.9241. Okay. Now you're going to do everything in the You're going to do everything in the parentheses before you add. So, and you can drop the sum of now because we have the numbers in here. So let me see. Let me pull up the calculator. Here we go. All right, so we have 6.015 times 0.0759. So it gives us 0.45, and we're going to round this to 0.457. So 0.457 plus, and now we're going to do the other parentheses. So this is going to be 7.016 times 0.9241. That gives us 6.48, and we're going to round this down to 3. 6.483. Okay, now you're going to add and just atomic mass. I tend to not write this down the left side, but you should. Don't be lazy with your math like me. Okay, and then we're just going to add those together. So clear. 0.457 plus 6.483 equals 6.94. Okay, so the average atomic mass for our unknown element is 6.94 AMU. Okay, and my challenge to you is to go ahead and go in your notes and figure out, using your periodic table that's in there, which element this is. And so the way you're going to do that is you'll look around the periodic table until you find a number close to this. And if that number is higher than this, you'll go to the left on the table. If it's lower, you'll go to the right until you find something that's like within, I would say plus or minus 0.1 AMU. Okay. To maybe 0.3 AMU. Okay, it should be pretty close. This is data from a real element. And so if you can figure it out, write it down in your notes and identify the element. All right. I'm going to stop sharing there. And that's it for calculating atomic mass. It's actually a pretty simple process. It just looks scary because there's a new math symbol involved. If you have any questions, please feel free to come and ask, and I can help you work through the worksheet with this.